So today we're going to talk about resonance and formal charge. So when we're dealing with resonance, what we're talking about is compounds that could have a double bond in more than one place. So for instance, ozone. Ozone is O3. We have a total of 18 valence electrons. So when we write out the structure, it's going to look something like this. Okay. Then when we add the electrons, it's going to do that. And then this side's going to have a double bond. 2, 4, 6, 8, 10, 12, 14, 16. And then we put a lone pair on the central atom. Okay. So here's my 18 electrons. And what happens with this compound is when they actually sit down and do a test and experiment on what's the length of these bonds, it's not the length of a normal double bond, and that's not the length of a normal single bond. They're actually the length of like a 1.5 bond. So who's to say that this double bond isn't over here or this single bond isn't over there? So it could really be in either location. So what we do is we draw what we call resonance structures. So the way we do this is we draw a double-headed arrow, okay, and then we draw the same structure but with the double bond in the other location. So it's almost like we flipped it over, but we didn't really flip it over. We just moved the double bond over to this side instead of over this side. So what this means is this Lewis structure isn't this isn't the correct Lewis structure. This isn't the correct Lewis structure. It's a combination of the two. So it's some sort of in the middle or hybrid version of the two. So some depending on the type of compound and which compound we're talking about, some compounds will have 2 resonance structures. Some might have more than 2. Some could have 3 or 4 resonance structures. And what you have to do is draw all of them depending on where the double bond is. So another example is, let me get it real quick. Another example of a resonance structure might be the carbonate ion. So CO3 -2. So we have 4 electrons from the carbon, 3 times 6 for the oxygen, plus the 2 because it's a -2 compound. If we have an ion, make sure you add. If it's negative, you would add that many electrons. If it was positive, you take it away. So 4 and 18 is 22, 24 total electrons. Okay, and so it's going to be C O O O, and it's going to look something like this. There's going to be a double bond on one of the oxygens. The other oxygens are going to be like that. But again, this double bond could be here, or it could be there. So when you draw it, you're going to draw another one, putting the double bond in the other location, and then still another one with it in the final location. And again, none of these is correct in and of itself, but remember, it's a combination of all 3 of these, because the double bond, or that extra pair of electrons, is kind of floating around within the rest of the compound. Okay. Now, there's other ones where we have to do what's called formal charges. So for some compounds, there's really more than one way that you could write that the Lewis structure. One example of this is the thiocyanate ion, which is SCN. Okay, SCN -1, that's a minus. So to count up the valence electrons, we have 6 from the sulfur, 4 from the carbon, 5 from the nitrogen, and then we have 1 because it's a -1 ion. So 10, so we have 16 total electrons. Okay, and again, there's really 2 ways of doing this. One is going to look like this with a triple bond between the nitrogen and the carbon. And then the other one is going to look like this with double bonds on either side of the carbon. And then lone pairs there. Okay, so technically both of these are written correctly, but which one is better? So what we do is we use something called formal charge. And formal charge, I'm going to just abbreviate it FC. There's a way to calculate it. So it is valence electrons minus lone electrons plus bonds connected to that particular element. So you can assign a formal charge to each element within a compound. So you count up how many valence electrons does it have, subtract the lone electrons around it plus the bond. So add these two together before you subtract that. So an example, and what we can do then is we can analyze which one has the more stable formal charges, and the stable formal charges would be ones that have the most, or the formal charges that are closest to 0. So let's go ahead and try this. So for this nitrogen, I know that nitrogen has 5 valence electrons. It has 2 lone electrons and 3 bonds. So 5 valence electrons minus 2 lone electrons plus 3 bonds. So 5 minus 2 plus 3, which is 5. So that would be 0. So we would assign a little 0 to that nitrogen. Carbon, I know that has 4 valence electrons. There's no lone electrons around the carbon. So it would be 4 minus 0, but there's 4 bonds. 0 plus 4. So 4 minus 4, that is also 0. Okay? Then for sulfur, sulfur has 6 valence electrons. There are 6 lone electrons and 1 bond. So 6 plus 1. So 6 valence minus 6 plus 1. So that would be a -1 for a formal charge for sulfur. Okay. If we go over here to this one, we know that nitrogen has 5 valence electrons. There's 4 lone electrons, 2 plus 2, that's 4, and then 2 bonds. So 5 minus 4 plus 2, so 5 minus 6 would give me a -1. Okay. And then for carbon there, we have a 0 formal charge because we have 4 valence electrons and 4 bonds, 0 lone pairs, 0 lone electrons. And then for sulfur, we have 6 valence electrons, 4 lone, 2 bonds, so 4 plus 2, 6 minus 4 plus 2 would give me 0. Okay? In this case, these two, because when we analyze this, we want to look for the most formal charges that are closest to 0. Okay? Since we have 2 that are 0 and 1 that's -1, these two structures would be identical as far as the most stable. So this would be, I wouldn't be able to choose one or over the other here. You might want to look at electronegativity maybe, But for the most part, either of these would be correct structures or the most stable structure for each one. Okay? All right, let's try another one with N2O. Let's try another one with N2O. N2O has, so 2 times 5 valence electrons plus 6, so a total of 16 electrons. All right, and there's really three types of ways that you can write this one. Would look like this. You would do 2 double bonds, and you might do one like this. Okay. Then you're going to have a lone pair there. You're going to have lone pair, or 3 there. Lone pairs, lone pairs, lone pairs, lone pairs, and lone pairs. Okay. So now let's figure out the formal charges here. Okay. So for nitrogen, we know a nitrogen has 5 valence electrons, 2 lone electrons plus 3 bonds, so that would be 5 minus 5, which is 0. It's good. 5, and then we have 4 bonds, no lone pairs, so 5 minus 4, so that would be plus 1. And then for oxygen, has 6 valence electrons, there's 6 lone electrons plus 1 bond, so that's 7, so 6 minus 7 is a negative 1. Now let's go to this middle one. The nitrogen, 5 valence electrons, 4 lone electrons, and 2 bonds, so that's 4 plus 2, so 6. 5 minus 6 is negative 1. Then we have 4 bonds, 5 valence electrons for nitrogen, so that would be a plus 1. Okay, and then this would be 0 here for oxygen, because you have 6 valence electrons, 4 lone electrons plus 2 bonds, so that would also be 0. Then we go here to this one. This nitrogen, 5 valence electrons, 6 lone electrons plus 1 bond, so that's 6 plus 1, which is 7. 5 minus 7 is a negative 2. This nitrogen in the middle is going to be 5 minus 4 bonds, so 5 minus 4 is plus 1. And then on the end, this oxygen, 6 valence electrons, 2 lone electrons plus 3 bonds would equal 6 minus 5, which would be plus 1. Okay, so I know that this one is not going to be the winner because I don't have any zeros here. Okay, and then really these two would be pretty equal. In general, this one is probably more stable because we know that nitrogen likes to make triple bonds. It likes to just have 1 lone pair in general. So I would go with this one being more stable. But again, either of these would be, technically correct, okay, or would be stable, okay. One thing to note, if you add up all the formal charges, they should equal the total charge of the compound. So if you look up here, our charge of our ion is -1, and when you add these up, it equals -1. This is a neutral atom, and all the formal charges add up to equal 0. So 1 plus -1 is 0. Plus 1, -1, -2, plus 1, plus 1, so they add up to 0. So if you did it right, your formal charges should add up to the total charge of the compound or ion. Okay, I hope this helps. Let me know if you have any questions.